So let us now consider operators. This will be linear operators. We talked a little about linear operators last time, in the last video, and want to remind you what you have here. First, there's the notion of a linear map between vector spaces. So you go from a vector space V to a different vector space W, and that's called a linear map. We considered, however, the case where you act on a vector space V and the operator, this linear map, takes you to the same space V. In that case, when you go from the space to the same space, we call the linear map an operator. So let's consider linear operators. And a good name for a linear operator is T. So a linear operator T, this is going to be a linear operator T, takes you from the vector space to the vector space. Now, what is the quantum mechanical motivation for this? Well, operators are crucial in quantum mechanics. They can do many things for you. So in particular, observables are represented by operators. When we talked before about the expectation value of an observable, we're really talking about operators, and these are operators, our linear operators. When you talk about symmetries, you use operators. When you talk about time evolution, the unitary operator that generates time evolution, we will be talking about operators. So operators are a key ingredient in quantum mechanics. And we said that this operator is a linear operator if it satisfies a couple of conditions. Two conditions, T on U plus V, where U and V are vectors in the vector space, is T of U plus T of V. So this is for U and V in the vector space. Moreover, if you have T on a number times U, the number can go out. The operator doesn't care and gives you this thing. There is an issue of notation here. Operator acting on a vector. So how should we write it? Should we write T of U? I didn't do that. I wrote T acting on U, and I think of this as a vector. You see, the operator acts on a vector to give a vector. So T acting on U is a vector, the vector TU. I could have called it the vector T of U, which is the image under this linear map of the vector U. So to simplify notation, I really just write it as T of U. And this also captures a conceptual fact that in some sense this operator is acting by multiplication on the vector, some kind of multiplication that we will have to understand. It's really matrix multiplication on a vector, but it's a good thing. On the other hand, for example, here I cannot avoid the parentheses, because if I had written T of U plus V, you would think this is T of U plus V. You wouldn't know whether T acts on U or acts on V as well, and this could be thought as this vector plus this vector, but here I mean the operator acting on the sum of vectors. So some parentheses you cannot avoid, and you better leave in there. So this is our notation. In this case, U is a vector, A is a number in the field that could be real or complex, and U is a vector. So a couple more remarks on this thing. This looks like a linear operator. To describe it completely, you should tell me how it acts on all the vectors in V. And that looks like an impossible task at first sight. The vector space has infinite number of vectors. You know that vectors that point in all directions of all sizes. So to define the linear operator, do I need to tell you how it acts on every vector, give you the infinite list? No. We will learn that it's enough to describe how it acts on a basis. Because since every vector can be obtained by putting together vectors on the basis, multiplying them by numbers, by these properties, if I know how the operator acts on the basis, you will know how it acts everywhere. So just describing how it acts on a basis is a finite set of information, and that's what the linear operator has. Another remark that may be of interest, and you may miss it if you don't think about it. What is t acting on the 0 vector? So what does the linear operator do on the 0 vector? Do I need to know what the linear operator is or not? Well, actually, I claim that the 0 vector is left invariant, so any linear operator on the 0 vector is the 0 vector of the vector space. You wish to prove it? It's actually not hard. You argue it the following way. You say, consider t acting on the vector u plus the vector 0. By linearity, this is t of u plus t on 0. I can put the arrow maybe just to make sure you don't think that's the number 0. This is the vector u and the vector 0. Now, this is linearity. On the other hand, let's go to the left and say, well, u plus 0, since this is the identity element for addition, this is just t of u, because this whole thing is u. And now you have an equation where you have tu is tu plus t0. You can cancel the tu's. That's legal and fine because on a vector space, every element has an additive inverse. So for tu, there's something you can add to make it 0. So you add that here, you add that on the other side, it's the equivalent of canceling, and then you get that t on 0 is 0. So this is an important fact about vector spaces and their linear operators. The linear operator always gives you 0. So let's consider examples. It's the best way to understand those linear operators. And our examples will be actually very interesting, all of them. Even the trivial examples should be made clear because the trivial examples show up all the time. So I'm going to consider, let me erase this little proof here, and consider examples. So the first example, I'm going to take the vector space to be the vector space of polynomials on a real variable. So the vector space V is the polynomials on the real variable x. So the vectors are simply polynomials, real polynomials of x. So the vectors are polynomials p of x of the real x. And we'll consider two operators acting on these polynomials. The operator t that will be the operator that differentiates the polynomial. So t acting on a polynomial will be the derivative with respect to x of the polynomial. So I write it as p prime. T acts on a polynomial and differentiates it. Now, you should think about this and see if you realize that this is a linear operator. Well, these things should be true. If you differentiate a sum of polynomials, well, it's the derivative of the sum. That's correct. And if you differentiate and you put the constant goes out. So this is fine. This is a good operator, a good linear operator. In particular, if you act on the zero polynomial and differentiate, you get 0. Another interesting operator is operator X, S, that acts on a polynomial by multiplication by X. S, acting on a polynomial, multiplies it by X and gives you another polynomial. So these things map polynomials to polynomials. This is also linear. If you multiply by X a sum of polynomials, you multiply each and sum, multiply, a constant goes through. So that's another linear operator. So two interesting linear operators on the space of polynomials. All right, so we have one example. Let's consider another example. Example number 2. For this, we will consider those infinite sequences as the elements of the vector space. So the vector space is V, is infinite sequences on a field. So it could be an infinite sequence of real numbers or of complex numbers. Let's take them to be real. There's no need to bother. So the elements of this thing are x1, x2, x3, infinite sequences where all the xi's belong to the field. We said real, so well, maybe I'll just keep it field and field. So the set of vectors are the set of infinite sequences. This looks like an infinite dimensional vector space. We discussed that and we said, yes, it's an infinite dimensional vector space. And it has two operations that are kind of interesting. So let's define L, which is going to be the left shift. And we can think of it as falling off the cliff. So you have this a cliff here, and here is x2, x3, and x1 is falling off here, the cliff. So you have the L operator acting on x1, x2, x3, gives you just x2, x3, x4. x1 fell off the cliff from the left. It's a left shift. So you move it to the left, but since there's nothing you can move it, it falls off the cliff, and that's what this is. It's a funny operator, but it's a linear operator. You can try it. You should write it. In fact, write L acting on this, and then add another vector, and you will see the first vector falls off the cliff, the first input, the second does. It's a linear operation. You multiply by a constant, it doesn't matter. So it's a funny operator, but it's a good linear operator. And then there is a right shift. And what is the right shift? R on x1, x2, x3. Well, now I want to push it to the right. This is sometimes compared to this famous and amusing concept of the Hilbert Hotel, in which there's a hotel that's an infinite hotel, and it's full. It's just full. But you come in, and it's late, and you have nowhere else to go. And the manager is a very clever person and always manages to find room for you by telling to people to do a right shift. So x1 says, go to the room of x2. x2 go to the room of x3. And they go like that, and they leave you room number 1 for you. So the right shift is something in which you sort of say to x1, go to the next, x2, go to the next, go like that. And you put something on the first, you create a space in the first one, so it's a right shift. Now, we're doing mathematics here, not hotel business, so what should we put here? We have to put the number. Suppose I put the number 1. Would it work? The number 1 has a problem. This would not quite be a linear operator. Remember, a linear operator on the 0 element should give you the 0 element. So suppose all of these are 0, and this would create all of those 0 but a 1 here. So it would not give you the 0 element. So this is impossible. The only thing you can put here is 0. So it's the right shift, and you must put a 0 over there. And this is a linear operator as well. Sounds surprising. These two operations are a little like inverses of each other, but maybe not quite either. One moves you to the left and you lose information, you lose x1. One moves you to the right without losing information. They're interesting things to do. So these are our linear operators that are of interest. Now let's take a third one. So these are the trivial operators that I'm going to do. 3 and 4 are simpler operators, and we want to understand them because they show up some places. So here it is, the 0 operator. I don't have a better name for it. You could put just another 0, so now we would have 3 zeros to be confused about. The 0 number, the 0 vector, and the 0 operator. But if we put a hat, maybe you think of a 0. The only problem, you may think this is an O, which is a good name for an operator, but at least here, just think of it as the 0 operator. What does the 0 operator do for a living? Well, not much. The 0 operator acting on any vector gives you the 0 vector. So it kills every vector, sends them to 0. And this is something you should, it's a perspective that you should have about these linear operators. If you have the vector space V and you have the linear operator, maybe the linear operator, here's another copy of the vector space V. The linear operator is supposed to take V to V, but nobody says it takes everything here to everything here. Maybe it takes all of this to just one element here, or it takes this to some fraction, or it does all kinds of things. So here is an extreme case in which the operator takes everything to the 0 vector that is sitting somewhere here, so everybody goes to the 0 vector. So this is an interesting operator, and it's a linear operator in a trivial way, because whatever you do, you get zeros and zeros and nothing happens. The last operator I want to discuss is the identity operator. And we call it I, like that. And also it's a simple operator. This operator acting on any vector gives you just the vector you started with. So it doesn't change any vector. It's an operator, but it doesn't do anything much except just what is the action of the identity operator on the vector v1? v1. On the vector v2? v2. On any vector does that. And then the conditions for linearity are satisfied. The 0 vector is sent to the 0 vector as it should be. So there we go. We have a collection of vector of operators that will give us the opportunity to test our concepts and see how they work.